Alrighty, this is day 2 of L'Hopital's, and this is where we are going to be talking about other indeterminates. So we know 0 over 0, and we know infinity over infinity, but now we have other indeterminates, such as infinity times 0, infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0 power. Now, if we have these types of indeterminate forms, we are going to make these into fractions and then use L'Hopital's with the fraction. So here we have the limit as x approaches infinity of x sine of 1 over x. Now, if I were to break this up into two limits right here, we have the limit as x approaches infinity of x, which is just going to be infinity. And then we have the limit as x approaches infinity of sine of 1 over x. So this essentially is a sine of 1 over some very big number, meaning that my argument is going to turn into 0. So this is going to be 0. And then sine of 0 is going to be 0. Since we have infinity times 0, this is indeterminate. Since this is indeterminate, we have to use L'Hopital's. Now, one of the rules for L'Hopital's to work is that we have to make it into a fraction. So this right here, this is not a fraction. But we can use some of our tips and tricks in terms of reciprocals to make it look like a fraction. So just a reminder, back in maybe Math 3, whenever we talked about reciprocals and whatnot, x right here is the same thing as 1 over x. If I were to do same change flip. Now that's going to be important because then I could say the limit as x approaches infinity of sine of 1 over x over 1 over x. Because remember, 1 over x is the same thing as 1 times x over 1, which is just x, based off of my little same change flip. Because now this is in the form of L'Hopital's, I could take the derivative of the numerator and the derivative of the denominator and see where that takes us. But first, obviously, you do want to make sure that you actually explicitly write that here, or else points will be taken off. So just make sure that you do that. Okay. The derivative of sine of 1 over x is going to be cosine 1 over x, and then the derivative of the inside, which is just going to be negative 1 over x squared. And then the derivative of 1 over x is going to be negative 1 over x squared. You'll see that these two will cancel out. So I'm just left with the limit as x approaches infinity of cosine 1 over x. Now, if I were to use direct substitution, and this is going to be a very big number because this is infinity, my argument is going to approach, plot twist, 0. So then I have cosine of 0, which is just 1. So this means that my answer for number 1, the limit as x approaches infinity of x times sine of 1 over x, is going to be 1. All right. We're going to do something similar to number 1, where we have that 1 over x, except we have something raised to an exponent of x. Now we have a function raised to another function. So remember that because we have something like this, we will probably most likely have to use something in terms of logarithmic differentiation. But before we do that, we need to see if it's in indeterminate form. If I were to use direct substitution, I have 1 over some very big number, which is just going to be 0 here. So now I have 1 over infinity, and 1 over infinity, or 1 to the infinity, is an indeterminate form. Since this is an indeterminate form, we can use L'Hopital's. Now, for this one right here, we are going to use logarithmic differentiation, like I said, because I have a function to a function. So in this case, I'm going to have ln of y is equal to the limit as x approaches infinity of ln of this lovely thing right here. But I'm going to bring down the x. So I have this right here. Okay, so then I know that if I were to use substitution, again, direct substitution, I have infinity times, let's see, that's going to be 0, because this is going to be 0, this is going to be 1, the argument's going to be 1, ln of 1 is 0, so infinity times 0, guess what? Indeterminate. Now, just like what we did earlier here with x, we are going to change that so it looks like this right here. All right, once we do that, we are going to take the derivative of the right side, because we're going to use L'Hopital's here. That is going to give us 1 over 1 plus 1 over x, and then times negative 1 over x squared. And then the derivative of 1 over x is negative 1 over x squared. That's going to cancel out, so you're just left with the limit as x approaches infinity of 1 over 1 plus 1 over x. If I were to substitute in a very big number here, this is going to be 0, so I have 1 over 1. So this right here is going to be 1. Now, here's your plot twist for the day. The right side has a limit of 1. So this is ln of y is equal to 1. But remember that y is this limit right here. So what we need to do is solve for y in terms of what we have so far to get my limit of this function right here for number 4. So using our basic math 3 skills, we are going to get y is equal to e to the first power, which means that the limit as x approaches infinity of 1 plus 1 over x to the x power is e to the 1. All right, I'm going to do one more in terms of something like that where we have to use logarithmic differentiation. So something like number 8 here. I have y is equal to the limit as x approaches 0 from the right, 4x plus 1 cotangent of x. Using logarithmic differentiation, because of a function to a function, I have ln of y is equal to the limit as x approaches 0 to the right of cotangent of x times ln of 4x plus 1. Okay, now if you were to think about cotangent of x, that's going to be, well, let's actually draw this right here. Cotangent of x looks like something like that. That's not pretty, but you know, you get the idea. And if it's 0 to the right, we know that this is going to be infinity. And then here, once again, ln of, let's see, 0 to the right. So ln of 1 essentially is going to be 0. So we have infinity times 0, which, guess what? It's indeterminate. Because it's indeterminate, we have to use L'Hopital's. But in order to use L'Hopital's, we have to turn this into a fraction. Well, good news. Remember that cotangent is the reciprocal of tangent. So I can actually rewrite this so that I have tangent at the bottom. And then remember, now we have to actually use or evaluate at 0 from the right to see that it is an indeterminate form. So thinking about tangent of 0, we know that that's going to be 0. And then thinking about ln of 4x plus 1, ln of 1 is going to be 0, so this is going to be 0, and this is going to be 0. Indeterminate. Yay. L'Hopital's. I'm getting lazy, but remember, don't be lazy on the AP exam, okay? You're trying to get 3s, 4s, and 5s, preferably 5s. So don't shorthand stuff and just write it out. Okay, once you do that, I'm going to take the limit of the derivative of this. So that's going to be 1 over 4x plus 1, 4. And then the derivative of tangent is going to be secant squared of x. Okay, so let's see if we could do something in terms of this right here. Using direct substitution, you are going to actually get 4 over 1 over 1, which is just going to be 4. So now you have ln of y is equal to 4. But remember that you want y, aka this right here. So if I were to do that, using our little trick that we learned back in Math 3, our limit here is going to be e to the 4th. All right, we would do more problems in terms of L'Hopital's for other weird indeterminate forms. And then you'll have more practice.